All right, so let's get started. So homework 6 is up online. Let's do on Tuesday. Okay, so only a few days now. Um, for in-seat classroom disinfection, today's assignment is for Ethan and Danny. Okay. We are going to still check into chapter 21. So last time we talked about Kirchhoff's rules. So you are using two rules here for complex circuits. Um, so one is called junction rule. That's if you encounter a junction, then the current go in equals to the current go out. Okay. And then for the loop rule, it says, yeah. So let's take it one by one. So this is junction rule. Okay. So the current goes in equals to current goes out. Okay. And then for the loop rule, if you start from one point, you pick any loop on your circuit, you'll go through one loop and return to your starting point. So then the change in potential should be equal to 0, all right? To determine the change in potential across each element, if you go from the negative terminal to positive terminal across a battery, then your potential increase. Otherwise, potential decrease. And then if you go, your loop goes in the same direction as the current going through a resistor, then the potential decrease. Okay. If your loop goes against the direction of current, then potential increase. Okay. And when you return to the initial starting point, you should get a change in potential equal to 0. Okay. And we also talk about the V meters, voltmeter, and ammeters, which you use to measure voltages and currents. Okay, so basically for ammeter, because it measures the current, and then you don't want to disturb the main circuit by putting an ammeter into it. So then the resistance of this should be very small. Okay, so because it will be always in series with the element that you are measuring, um, that you want to measure the current. Okay, so an ammeter will be in series with the elements, and then in that case, resistance is very low, so it's easy to burn it. Okay. On the other hand, if you have a voltmeter that measures the current, the voltage, so it's always in parallel with your element that you are measuring the voltage across. Okay. So in that case, you don't want to have the current going through the main, like for the current to go through this V meter. So you want to keep this current going through it as small as possible. So you want to have resistance of this as large as possible. Okay. So a V meter has very large resistance. Okay. All right, and then we mentioned for also for ohm meter, it measures the resistance of a resistor. You guys don't use this in the lab, but if you want, you can actually try to use it just to measure a resistance of your interest. Okay. All right. Um, so today we are going to look at some another type of circuit which you have both a resistor and a capacitor in the circuit. Okay, so in this case, so then there's a resistor here, there's a capacitor here that are in series. Okay, and there's a power supply in the circuit. There's a switch. Okay, so the moment you turn on the switch, okay, so then the current is going to be going from the positive terminal. That means positive charge will flow through there, or flow will start flowing starting from the positive terminal over here. So then you will have positive charge built up on here and then negative charge built up on here. Okay, because for a capacitor, you have two conductive plates parallel to each other but not in contact, right? So this is an open circuit. It's not a closed circuit. So then the current will not go through the capacitor unless you have a lot of voltage. Okay, if you reach the breakdown voltage of the insulation, then there will be current, but otherwise there will be no current. Okay, so if not specified, then we'll assume that current is small. It's not, you're not having current going through the capacitor. Okay, so you'll have charge build up on the plates here. Then there will be potential build up across the plate. Okay, and then you at some point later you'll reach at the point that when the potential across the capacitor is the same as the potential provided by the battery. So then there will be no more charge flowing from here to here, right? Because now these two are equal potential, so no more charge flowing. So then you have charged your capacitor, all right? So in that sense, then capacitor now will have charge and potential build up, okay? It can be demonstrate how much charge you can build up, okay? So to demonstrate this, we need to use the calculus knowledge. So I'm not going to show it here, but if you want to know, then you can actually derive this equation from calculus. Okay, so the charge built up according as a function of time t. So q parenthesis of t, that means charge as a function of time t. That will be equal to the capacitance of the capacitor times the potential the battery can supply. So the electromotive force E, all right? Or sometimes you see people just write as V, so CV, okay? And then 1 minus exponential to the minus T over this tau, it's a constant, all right? That's equal to the resistance of circuit times the capacitance of the capacitor. Okay, so tau is equal to R times C. And this is a time constant. So this would be in second. Okay, so if you have R in ohms, C in farad, then you will have second. Okay. All right. And for the voltage as a function of time t, it's equal to epsilon EMF, the epsilon 1 minus E minus T over RC. Okay, so basically these two are proportional to each other with a factor of C, the capacitance, because if you do voltage, if you do charge divided by voltage, it gives you capacitance. Okay, so this is for the charging process. Let me see. So in this case, you can see if your t equal to 0, all right, your charge equal to 0. Okay, so when you when you just start charging, then charge will be 0, and then it will build up. Okay, and then it kind of saturate exponentially up to that. Okay, so let's take a look on the first example here on charging a capacitor. So it says the switch on an RC circuit is closed at t equal to 0. Given that epsilon equal to 6 volts, R equal to 92, and C equal to 28 microfarad, how much charge is on the capacitor at t equal to 4.0 milliseconds? Okay. So this is charging a capacitor. Then there are two equations here you might want to use, the charge and then also the voltage. Okay, we are looking for a charge here, so you just use the q as a function of t equals to c times epsilon 1 minus e to the minus t over tau. Okay, where tau is equal to r times c. Okay, I think I can have you guys calculate for this, and then we can take a look at the solution in a couple minutes here together. Okay. All right, so I think you can just plug in the numbers here, but one thing to pay attention is the units given. They are not all in SI unit. Okay, so epsilon is equal to, or C is equal to 28 micro for us, so means minus 6. Okay, epsilon is 6.0 volts, and then 1 minus exponential of minus t. T is given as 4.0 milliseconds, so minus 3. Okay, divided by where this tau constant is R times C. Okay, so R times C, R is 92 ohms, and then C is again the 28 times 10 to the minus 6 for R. Okay, all right, and then you probably want to be careful when you plug in those numbers into your calculators. Okay, so at the end this would be 1.32 times 10 to the minus 4 coulombs of charge. Okay, or you can say it's 132 microcoulombs. Okay, if you move twice over, then minus 6. Okay, all right. So if you charge a capacitor, if you plot it, okay, so this is what it's going to look like. The voltage on the capacitor will increase, okay, and then saturate at some point later, okay. So when your time t is equal to 4 times of the time constant tau, then you are already at about 98% of the full voltage, okay, that the battery can supply. So typically we can say, yeah, so that gives you a sense how much is that. So for one time constant, after one time constant, it's already 63%, okay, in that sense, okay. So usually in the lab, we can just stop at 4 or 5 times of the time constant, okay. So you guys will be doing the RC circuit lab the week after the break, okay. Now this is V, the Q will be the same, the charge on the capacitor will be the same, similar curve, it goes up exponentially and then saturated, okay, about 4 or 5 time constants later, okay. However, the current in the circuit actually will decrease, okay, so you'll start to have larger current, okay. So this is current, it's equal to initially it's equal to epsilon divided by R, then it decreases down, okay, to about 1% up to 4 times our current constant, okay. So just keep in mind the charge goes up, the voltage goes up, but the current goes down on the capacitor, okay, or in the circuit here. And then this is given by epsilon divided by R e to the minus t over tau, okay. All right. So one of the applications for a RC circuit is in the traditional digital camera with a flash. The flash unit should have a circuit like this. Okay. So this is the battery of the camera, and then for the flashlight is provided by this light bulb over here, and you will charge the capacitor. Okay. And then after this is charged, you'll turn on this switch to release the energy stored in this capacitor, so to fire the flash. All right. So you can see actually it will take a little bit of time to charge the capacitor each time, right? So that's if you ever had the experience like taking pictures just one by one very quickly, one after another, you'll find that sometimes you'll not be able to fire the flash because it takes some time, okay, to charge the capacitor. All right, but let's take a look on this figure here. On this problem here, it says the figure on the left shows a simplified circuit for a photographic flash unit. This circuit consists of 9 volts battery and a 50.0 kilo ohm resistor, a 140 microfarad capacitor, and a flash light bulb, and 2 switches. Okay. Initially, the capacitor is uncharged and the 2 switches are open. To charge the capacitor, switch is closed, S1 is closed, switch 1 is closed. To fire the flash, S2 is closed. Okay. It says how much time does it take to charge the capacitor to 5.0 volts. Okay. So that means you close this one and then calculate how much time it takes to have the potential across the capacitor to be 5.0. Okay, so in this case, you are using the other equations that we got for charging a capacitor. So it will be the other equation of V on the capacitor as a function of time t is going to be equal to epsilon times 1 minus E minus T over tau. Okay, tau will be R times C. But this time you're looking for T. Okay, so you're solving for T this time. Okay, give it a try and then we can take a look at the solution together in a little bit. So basically it gives you V, this V equals to 5, okay, 5 volts. This is 9 volts. And then it gives you R, it gives you C. So R is the 50 by kilo ohms, and then C is the 140 microfarad. Okay, so you solve for T. Okay. All right, so let's see how to solve for t here. So your t is in this exponential function. Okay, so you want to first just figure out what's the value for the exponential function there. So it's 5 volts equals to 9 volts times 1 minus exponential of minus t over r times c. Okay, so you can calculate what's r times c. R times c is the 50 kilo ohms, all right, times 140 microfarad minus 6. Okay, that will give you 7 seconds. Okay, exactly 7 seconds there. All right, so this r times c is 7. Okay, so then you divide both sides by 9. You have 5 over 9 and equals to 1 minus e exponential of minus t over 7. Okay, so then exponential of minus t over 7 should be equal to 4 over 9. Okay, because 1 minus 4 over 9 will be 9 over 5 over 9. Okay, so exponential of minus t over 7. All right. Now you want to get rid of the exponential function. All right. So exponential function, to get rid of it, you do natural logarithm of both sides of equation. Okay, so do ln of 9 over 4 should be equal to ln of exponential of minus t over 7. Okay, so in that sense, the ln function and exponential function will cancel out. Okay, so then minus t over 7 is equal to ln of 4 over 9. So your t will be equal to, you multiply both sides by minus 7. Okay, so minus 7 multiplied by that. And it tells you your t is equal to 5.68 seconds. Okay. All right. Let me know if you have questions. Okay. All right. So if you want to fire the flash, you actually discharge the capacitor. Okay, so this is what happens. So if you turn on the switch, then the voltage and charge built on the capacitor will go through this resistor. So basically, in that case, the resistor consumes your energy and charge out of the capacitor. So then the voltage that built on the capacitor will be decreasing this time. Okay. And similarly, again, after about 4 times of the time constant tau, your voltage and charge will decrease to about 2 or less %. Okay, so at that time you can consider that the capacitor has been discharged. Okay, so for the voltage and then for the Q will be the same, exponentially decay. Okay. And then one more note maybe on the current. So the current will start out as V over R and then decrease as well, exponentially decay. Okay, so in this case, current is similar to voltage because current will be equal to V divided by R. Okay. All right. Okay. So far we have been talking about the direct current circuit. Now in our daily life, a lot of times you have actually alternating current. Okay, So like the household volt electricity, it's an alternating current. So for that, the current, the voltage of the electricity actually varies, okay, as a sine function, okay. Or if you want, you can use a cosine function. They are the same basically, okay. So then V is equal to a peak value times the sine function of omega times t, where omega is the angular frequency, all right? It refers to the frequency of the electricity, okay? So for example, we have 60 hertz. Then this is 2 pi over the 60 hertz, okay? Or 2 pi times the 60 hertz, okay? Now, according to Ohm's law, V equal to I times R. So then I equals to V over R. So for the current, it should also have a peak value. Okay, so it's the V peak over R as the peak value, and then times the sine of omega t. Okay, so we'll just use sine function here in this textbook. Okay, so you can see your voltage and then your current. They are sine function. They have peak value. All right. Now, for the voltage and the current, okay, if the peaks they happen at the same time, meaning if the current voltage is having peak, then the current is having peak. So then we call them, the two are in phase. Okay, so they peak at the same time, they have minimum at the same time. Okay, and then they have negative peak at the same time as well. Okay, so that's in phase. Otherwise, if the peak of the two, they do not happen at the same time, we call them have a phase shift. Okay. All right. Now, if you take average of either voltage, the potential, or current in the AC circuit, you will realize because it's a sine function, so you will average to 0, all right? And so that doesn't tells you how much electricity you are consuming, right? For a certain, like say, appliance, or like a certain element like light bulb, okay? So instead, we will be using root mean square quantity here, okay? So the root mean square quantity, we learned this already. So it's the square of that quantity, and then you take average of that. That means the 1/2 of the maximum square in this case, because it's a sine function. Yeah, over here. Okay. So if you square it, and then the average would be 1/2 of that. Okay. And then you take square root of that. That gives you the root mean square quantity. Okay. So basically, it's square root of this guy, 1/2 x squared maximum. So then the root mean square will be 1 over square root 2 of the maximum value. Okay. Which is little, it's about like let me see, maybe 70% of this. Okay. All right. So in that sense, then you can calculate the consumption of the power. So calculating the power and then find the average. Okay. So if you have a resistor in the AC circuit, then power is equal to I squared times R, where the I squared is equal to a peak value square times sine of square. Okay. So then for the average of the power, you average this expression, right? So I square peak, you average that, that's still I square peak. It's a fixed number, R is fixed number. Then you are really averaging the sine function here, sine of omega t square, okay? So if you do sine function square, then this is what it is. And then if you take the average, it would be 1/2, okay, of the peak value. Okay, so this is 1/2 of peak value. That would be equal to, if you are using the root mean square, okay, because root mean square quantity is 1 over square root 2 of the maximum, okay. So then it becomes, if you square it, it becomes 1/2 of maximum, okay. So the average power consumed by a resistor in the circuit is I square root mean square quantity times R, okay. And if you want to express that with V and R, so then you do for a resistor, power is equal to V squared over R. For V, you can take V peak times sine, right? Then you square, then so it's V squared sine square over R. Again, if you want to figure out what's the average power, then you average those, that's this expression. So then V squared still remains over R because they are constant numbers. And then you are just averaging this changing quantity here, okay? Because this is a function of omega t, it changes with t. So similarly, sine square omega will be 1/2 of the peak value, okay? Then it's V square, the root mean square quantity over R, okay? And then also the average power you can also write as just V RMS times RMS, okay? So for AC circuit, basically you'll be using the RMS quantities, then the power consumed will be similar to what we have in the DC circuit, okay? So P is equal to either V squared over R or I squared times R or V times I, okay? Now, one thing to take note is, so when we say our household AC voltage is 120 volts, that means it's the RMS value, okay? So that's the root mean square value. So the peak value is about 170 volts, okay? So it's more, potentially more dangerous than 120 volts, okay? All right, so let's take a look on one example here. It says, what's the peak current through a 500 watts room heater that operates on 120 volts AC power? So you're looking for I peak. Okay. So IRMS is equal to 1/2 square root of the peak. So that means if you can find out your RMS current, you can find your peak value for the current. Okay. Now it tells you the power is equal to 500 watts. Power, there are three equations, right? You can use V RMS square over R. You can use I RMS square times R. That's the power, the average power, okay? And then also you can use V RMS times I RMS. All right. Now the problem tells you VRMS. That's 120 volts. All right. So we are given P, and then we are given V RMS. Okay, so we probably can use this equation. P equals to this equation, V RMS and IRMS. Okay, to solve for the IRMS. Then after that, you can put IRMS over here to take your peak value. Okay, so from here we can see I peak is equal to square root of IRMS. Okay, and then from here it will tell you IRMS is equal to P over V RMS. Okay, so then this would be square root 2 of P over V RMS. Okay, and you can have your numbers in now. P is 500 watts divided by 123 volts. Okay, that will give you your I peak. Okay, so I peak is equal to that 5.89 amps. Okay, that will be your peak value. All right. Let me know if you have any questions on this one. Okay. All right. So if not, we will move on here. Now, for this next topic, we'll be focusing on electric flux and Gauss's law. Okay. So just to give you a heads up that this is not a section in the textbook. Okay, so you may want to take more notes on this one. But basically, this is a section, something you can look it up online. Okay, so there should be a lot of places that has this information on Gauss's law and electric flux. Okay, so basically, we can introduce a quantity called electric flux, and then we can utilize that to calculate electric field more easily for some complicated scenarios. Okay, so we'll take a look on first the definition of the electric flux. All right, so the flux, electric flux, this is a measure of electric field perpendicular to a surface. Okay, so if you have an electric field perpendicular to a surface, then you do E times A, all right, to be the flux, basically. All right. Now the angle here, a cosine of theta. Okay, so if you have E perpendicular to the surface, then angle is 0. So cosine of 0 is 1. Okay, so the theta is the angle between the electric field and the normal direction of the surface. Okay, so just keep that in mind. That's the normal direction of the surface. So normal direction and the E field are in the same direction. This case, if they are perpendicular to each other, then flux is E times A. Now, if you have electric field in this second scenario parallel to your surface, all right, so then the normal direction and the electric field has an angle of 90 degrees. They are perpendicular to each other. So normal direction should be in the vertical direction. Electric field is in the horizontal direction. So they are perpendicular to each other. So theta will be equal to 90 degrees. Okay, in that case, cosine of 90 degrees is 0. So then electric flux is 0. So basically, again, you don't see any like electric field going through the surface there, right? Because they are perpendicular to each other. Okay. In general, the electric field and the normal direction of the surface should have an angle. Okay, so if they are tilted, or if the surface is tilted, so then this angle theta is not 0 or 90 degrees. So then in general, you'll have a cosine of theta there. Okay. The SI unit for flux is newtons over Coulomb. So newtons over Coulomb is the E field, unit for E field. Area has meter square. Okay, so this is Newton times meter square over Coulomb. Okay, for the SI unit of it. Okay. And then in this case, you can think about this if you take the component of electric field that is parallel to the surface and then another component that's perpendicular to the surface, right? So for the component that's perpendicular to the surface, then it will have flux of E cosine A in that case. You can understand in that case. And then for the component is parallel to the surface, it will have zero electric flux. Okay, so then overall it should be E cosine theta A, which is the same as EA cosine theta. All right. Now, if you have a surface that this enclosed, it's closed surface. Okay, so for example, if you have a spherical surface, okay, or if you have the surface of a cubic shape, the 6 sides of the cubic shape, okay, so those type of surfaces are called closed surface. Now, in that sense, the sign of the flux is as this follows here, okay. So the flux is positive for field line that leaves the enclosed volume of the surface. Okay, so maybe I can give you an example here. So say if you have a cubic, all right, and then if you have electric field, if you have cubic like that, if you have electric field going in that direction, all right, so then on your top surface over here, the electric field lines or electric field leaves the surface. Okay, so then on the top surface, the flux through this one is positive. Okay, at the bottom surface over here, because the E field goes into the bottom surface, right? So then on the bottom, flux is negative. So flux is negative on the bottom, flux is positive on the top. Okay, so this is the convention here. Okay, but you can see in this case, if you add the two up, okay, then negative plus positive, the same magnitude, it should give you 0 flux overall. Okay, for those 4 side surfaces, they are parallel to the electric field, they will all give you 0 flux. Okay, all right, so this is a sign convention of when the flux the sign of flux. Okay, so if electric field leaves the surface, then flux is positive. If it enters the surface of the closed surface, it's negative. So with that, we can take a look on what will be the electric flux for a point charge. Okay, and then if you have a spherical surface that's a distance r away. Okay, so in this case, you can calculate what's the E field at distance r away for a spherical distribution over here. We know that for a point charge, electric field is kq over r squared, right? So E is equal to kq over r squared for a point charge at the distance r away from the point charge. That's the electric field. Okay. Now for the spherical surface, its area for a sphere, that should be 4 pi r squared. Okay, so then 4 pi r squared. In this case, at any point on the surface here, you can see the flux leaves the surface. Okay, and then at that point, the normal direction is the same direction as the flux. As the electric field. So theta is equal to 0. So that means flux is equal to E times A at any point. Okay. So then overall, the flux is equal to Q. Simply, you can see here, the R squared and R squared will cancel out. Okay. And then K. So if you remember, this K is equal to, for the constant K, that's equal to 1 over 4 pi epsilon naught. Okay. So then flux equal to E times A equals to K Q over R squared times. So this is E. For the A is 4 pi R squared. So R and R cancels out. Okay, you can replace K with that one. So it's 1 over 4 pi epsilon 0 Q times 4 pi. So 4 pi and 4 pi and will cancel out then. Okay. So then the flux will be equal to Q over epsilon naught. Okay. So this is then the conclusion if you look at a point charge. All right. So the flux is equal to Q over epsilon naught. And it doesn't depend on the distance where you are at. Okay. Your interest, point of interest is at. So that's that. So that's basically Gauss's law. Okay. Gauss's law says the flux of a surface, enclosed surface, in this case, a spherical surface, okay, is equal to the charge that surface enclosed divided by epsilon naught. Epsilon naught is the constant of 8.85 times 10 to the negative 12, okay, the permittivity of the free space, okay. So that's Gauss's law. Gauss's law says the electric flux through a closed surface is proportional to the charge close by the surface. In mathematical expression, this phi equals to, phi stands for flux, equals to Q divided by epsilon naught, okay? And then that has the same SI unit of newtons times meter square over C. Now, we use just Q. So that means if you have positive Q, right, you'll get a positive flux because then this, the electric field lines leaves the surface, okay? For the negative Q, you'll get negative flux because if you have negative charge, the electric field points towards that. So then it enters the surface, will give you a negative charge, okay? So your flux could be positive, could be negative, depending on your charge there. And although we derive the Gauss's law from a point charge with a spherical surface, so it applies to any shapes of surface, okay? So even an irregular shaped surface like that, okay, if it encloses charge, then it will have a flux given by this Gauss's law, Q over epsilon naught, okay? So for Gauss's law, we can take a quick look on one example here. It says a surface encloses the charges Q1, Q2, and Q3. It says find the electric flux through the surface. So Gauss's law says phi equals to Q over epsilon naught, where epsilon naught is 8.85 times 10 to the negative 12. That's in the unit of Faraday-meters. All right. So this time you actually have 3 Qs, okay? So in that case, you need to add them up, okay? So then flux will be equal to Q1 plus Q2 plus Q3 over epsilon naught, okay? So then 3.2 for Q1 times 10 to the minus 6 coulombs, the microcoulombs, plus 6.9 times 10 to the minus 6, okay? And then plus minus 4.1 times 10 to the minus 6 coulombs. All right, you keep the sign of negative there. Divide by 8.85 times 10 to the minus 12 Coulomb square over Newton times meter square. Okay, so your flux will be equal to 6.78 times 10 to the fifth Newtons times meters over coulombs. Okay, in that case. All right. Any questions you guys might have? So if not, then on Monday we are going to take a look more on application of Coulomb's law on how to calculate electric field by applying Coulomb's law. Okay. All right, we'll stop here for today then.